We are now going to move on to two other components besides resistors that are commonly used in circuits. And if you've had any exposure to circuits before, I'm sure you've seen these components. They are pretty much present in almost any circuit that you would build. So the first one here is our objectives today is that we're going to understand the voltage current relationships for a capacitor, which does require a little bit of mathematics that we don't necessarily have at this point, but not to worry, we're going to kind of simplify things so we don't need that mathematics at this point. But then we're also going to look at the fact that really a capacitor, in a lot of sense, you can think of as an energy storage device. And when we think of that, I'll show you an application on when we would use a capacitor, like an actual real application of it. So let's first look at a symbol here for capacitors. There's really two symbols there that can be used. There's just the straight parallel lines here, and I'll do plus minus some voltage and then some current going through it. But then there's another one here where it's got a kind of curved side on the second one instead of it being just a straight line. And again, we have a voltage and a current going through it. Now, the reason the difference between these, some authors just use this symbol all the time. Some authors use this symbol all the time. I like to use the symbols, and this is what sometimes circuit simulators do, that these are usually types of what are called ceramic or disc capacitors. And these are often electrolytic capacitors. Now, as far as how they behave as far as the current voltage relationship, there's no difference. The difference here is how they are manufactured. And the key thing here is ceramics have no polarity, which means you can put it in any direction. It's like a resistor. It doesn't matter what orientation. You can rotate a resistor 180 degrees and that doesn't do anything. And the same thing with ceramic or disc capacitors. You can rotate them 180 degrees when you're putting them in a circuit, nothing happens. But electrolytics capacitors have polarity. And when we say polarity, there is a right and a wrong way to connect these electrolytic capacitors up. The curved side is always representing a negative, meaning you need to attach that to the negative side of whatever your voltages are, or attach it to the ground, however the circuit. So there's absolutely a correct and a wrong way to wire up an electrolytic capacitor. And what will happen is they can or will blow up or pop if you put them in the wrong way. And if you've ever seen that happen before, sometimes even putting them in the right way, you can pop them if you exceed their voltage rating. So there's ways to get these. So ceramic disc capacitors, doesn't matter how you put them in. Electrolytic capacitors, they do matter. So these are the circuit symbols that we have here. I tend to always use this one regardless of whether it's going to be capacitor, whether it's ceramic or electrolytic, as far as when we're doing circuit analysis, but it's important to recognize the difference. Now the other thing, of course, just like we have a resistance labeled for a resistor, we have a capacitance for each capacitor. So C is my capacitance. And obviously it's going to tell me something about this. The units are in farads. And now typical values for PCB caps. So caps on a PCB board, on a printed circuit board. So, like on a motherboard or things of that nature. It's not to say that you don't use bigger sizes than this, because there's absolutely applications. They're in the microfarad to picofarad range, are what we would consider, quote, typical or realistic values for them. Now, that's not to say that you can't get millifarad capacitors. There are millifarad capacitors. Those tend to be used for high power applications, and they actually are very dangerous, those larger caps that can in the millifarad range, because the amount of energy they can store can actually kill you if you aren't careful with discharging the cap. So depending on the size of the capacitor, they can be actually very dangerous as well. Now, the stuff we're going to be using in the labs is all safe. You don't have to worry about that. The microfarad to picofarad range, worst case is that, if it's charged up, you might get a little bit of a, and if it's charged up and you short yourself across it, worst case scenario would be that you get a little like a little shock or something. It's not going to be any kind of, and you'd have to purposely do that. You're not going to accidentally do that with the stuff we'd be looking at in the lab. All right, but we need to get back to our goal here of understanding the current voltage relationships. Now, unfortunately, there's not a very simple current voltage relationship for a capacitor. So the current is equal to the capacitance, and then I'm going to write something here that most of you are probably not familiar with, dV over dt. Now, this stands for the derivative of the voltage with respect to time. And let me just give you a couple formulas here, because this is something that you talk about in calculus here. So, but let me just give you some formulas. And I'm just going to give these here. And I'll go ahead and say, for instance, if this was the voltage, this is the derivative of the voltage with respect to time. E to the kt. So k is just a number, t is time, representing, okay, I've got some time elapsing. The derivative of this is just simply k e to the kt. So it's actually a really simple formula. In calculus, you'll learn why it's like this, but for us, if we're just talking about having a formula, well, we know what an exponential function is. Oh, to take the derivative of it, I just take whatever this number is, including if it's positive or negative. So the negative or positive sign would come with it, and I just put that down in front of the exponential function. So that's just my formula for a derivative of an exponential function. Now, I know some of you probably haven't had trig yet, and we're going to do a little bit of trig, but don't worry, we're not going to do a lot here. We're going to do some very basic things. And I'll make sure to go over any details, because there's only really two other kinds of functions we're going to look at here in these simple cases. Is that, well, what if we have the sine, and again, I'm going to write this as kt. Well, the sine of this becomes the cosine of kt. And I forgot there's a k out in front here. So it does change. It goes from a sine function to a cosine function. But then again, I just pull that k kind of out in front here. And then there's one other one we'll look at here. And we'll do some examples with this in a later lesson here. And if I do this derivative of the cosine of kt, I get almost the same. You might even have guessed this, that, well, if the derivative of sine is cosine, you might guess that the derivative of cosine is sine, and you're almost correct, but we have a negative coming out here. So I have negative k sine of kt. Now, some of this you might say, I don't understand what you did here. Just look at these as formulas. That if you know that the voltage is e to the kt, then we know that the derivative of that is k e to the kt. So that means we can determine what the current is, because we now have a formula. If we know what the voltage is, we can determine what the current is, because we know how to do the derivative for these simple functions, and then we just multiply it by the capacitance. All right? Now, there is one other way to write this here. We can write, instead of writing it as current is equal to capacitance times the derivative, you can actually write this in terms of the voltage, and you get 1 over c integral of the current. So this is another thing that, again, you might say, I have no idea what this is talking about. Don't worry about it, we're not going to use it, but I just want to, for completeness, make sure that we understand this other relationship here. So when you do actually approach this in some of your other courses, especially some of the math courses, you'll say, oh, I remember him mentioning that. This is an integral. And again, it has something to do with calculus. And without really going into too much detail, essentially you're just undoing a derivative. So you can look at this table and essentially you're just going backwards on the table. But we're not going to really deal with this particular one here. We're going to only focus on examples that would cover that. All right, so that's the current voltage relationship for a capacitor. We are going to talk about the energy that can be stored in a capacitor. But before that, let's talk a little bit about how a capacitor kind of looks here, or the way a capacitor can be made. Technically, you could all make capacitors at home. They wouldn't be exactly very good capacitors, but you could do it. So what we have here for a capacitor is, imagine, and this is why we have a symbol here. So this is like a metal plate. You can kind of see where the symbol is going to come up with here. This is a metal plate here. And then I have another metal plate. And then what we have inside here, between these metal plates, we have something that's called a dielectric. And this is actually an insulator. Often, they might have paper, for instance. You can use paper as a dielectric for this to make a capacitor. There's other materials you can use as well. But basically, we can think of this as, okay, well, here's my capacitor. I've got some voltage here, and then I have some current that I'm wanting to go through here. Now, just from kind of a natural state here, we can say, well, wait a minute. Current, if this is an insulator, this is, current's, quote, not going to flow through an insulator. So what's going to happen instead is like, well, the current comes here, and instead what happens is I build up a bunch of positive charge on this top of this plate here, because the current isn't, quote, flowing through the capacitor. And then, well, if we think about this, positive charge is going to, if I got a bunch of positive charge up here, that means to balance the charge out so that I don't suddenly create, new charge, I'm going to have negative charges located down here. And basically what this gives me is this will give me some kind of an electric field. Now, if the voltage is changing, the amount of charge that is present on these planes changes, so there is a current then that is formed due to this electric field. Now, that requires a lot more math and a lot more physics, which we're not going to go in. But just know, if you change this voltage, you're changing the charge on these plates, and so you do have a current flowing due to the electric field. Now, the way to make your own capacitor at home, take a sheet of paper, and you need a graphite pencil, and shade one side of the piece of paper with your graphite pencil, making sure you don't punch through it, and then with the same pencil shade the other side of the paper, again making sure that you don't punch through it, and actually you've just made a capacitor. And it's actually kind of cool. You've made a capacitor, and you could actually measure the capacitance on it. You could hook it up and actually run a circuit, with the capacitor. Now, as I said, it'd be a terrible capacitor, but it technically would be a capacitor because you got a metal plate, which is the graphite, on the top side, and a metal plate on the bottom side, which again is the graphite, and then your dielectric, your insulator, is the paper that's in between those two metal layers. And you might say, well, wait, metal, I mean, graphite's not metal, it's carbon, but it's conductive. That's the idea behind it. All right, so that's kind of a little bit about this, but because of this here, if we think about if we have a DC voltage here, then the voltage is not changing. And if the voltage isn't changing, we just said if the voltage is changing, that's how we can get a current. So if the voltage is not changing, then we have no current flowing. Now there's a big assumption here. We assume the capacitor has charged up. There is a finite amount of time to charge a capacitor. Now, when I say finite amount of time, the time it depends on the circuit, depends on the size of the capacitor, depends on other resistive elements in the circuit. But for capacitors that we're talking about, again, on circuit boards, for instance, you're talking probably in the millisecond at the largest amount of time it would take to charge up the capacitor. And in some cases, you're talking micro and nanoseconds. So yeah, it takes time to charge it up. But if you're talking about, like milliseconds to charge it up, if you're putting a DC voltage on it, well then, it pretty much just is, charged up almost immediately. So with a DC voltage here, so if there's no voltage changing, no current flowing, with a DC voltage, applied, a capacitor behaves as an open circuit. Now again, I'm emphasizing this is DC, not AC. Okay, so, but what does that mean here? So it's an open circuit. But what that means is we've actually have energy stored in the capacitor. And there's a formula for the energy stored in the capacitor, and it's actually a very simple formula. It's like an omega, not a W. It's the Greek, which looks like a W. It's a Greek letter, omega, lowercase. Omega sub C, just for capacitor. This is equal to 1/2 the capacitance times the voltage squared. And then this would be, the units of this is in joules. And we're going to go through some examples, don't worry. We're just, as is normal, we kind of talk about all the theory, put down formulas, and then we'll do some examples. So we have energy stored in the capacitor, and this is the energy now that's stored in the capacitor. But what this means is we can use this energy to power circuits. So let me give you an example of a purpose, and you'll see this often in circuits with any kind of chips, any kind of integrated circuit chips. So let's just draw a chip here. I'm just going to draw an 8-pin chip. So I've got 1, 2, 3, 4, 5, 6, 7, 8. And I'm just going to go ahead. This is how the chips are normally numbered. Often, and that's not always the case, but often this would be, let's say, power. So I'm going to say this is my power supply. V power, actually we usually often, one way we write this is like VCC or something. So that's my power supply to turn it on. And we'll just make pin 4 the ground here. So this would be then attached to ground. So that's to power the chip up. And for instance, this could be like an op amp, for instance. And so this is how I power the op amp up. And then, I have other connections going here. But what's often done here is having it like this is not necessarily the best thing, because if you're thinking about how a circuit board is laid out, the power supply might be all the way over here. Okay, and so this is my power supply, so I have to run this all the way over to the power supply. Okay, so now anytime this chip needs more power, needs more current to do whatever it is, like for instance, if it's an op amp and you're like needing to, you're amplifying an audio signal, those things are going up and down, and so it's having to change its state rapidly, so it's needing current to do that. It's got to go all the way back to the power supply to pull that energy from that power supply and pull it down this entire trace here. Now what is often done instead here is what we do is we say, okay, what I'm going to do is put a capacitor here. And these can be somewhat large depending on the size of the chip and what the manufacturers, they sometimes even tell you what you should put on this if you read their data sheets. Sometimes they tell you what size of capacitor you should put on these. And I'm putting this capacitor, now on a circuit diagram I could put this anywhere, but I'm trying to show here that this is literally on a PCB board. That's redundant, but on a PC board, this would be located physically close to the chip. Because now, this is a DC voltage, so I've turned the power supply on, and we say, well, wait, this charges up almost instantaneously, so this has energy stored. And now, this chip needs some energy because it's doing a switch in states or something like that real quickly, and then instead of having to go all the way back to the power supply to get that energy, it can just tap into this capacitor to get the energy that it needs, and then it goes back here, and you say, okay, well, you're losing the energy from the capacitor. Well, that's why you have maybe a large capacitor. The larger the capacitor, the more energy you can store. And then, well, what happens is, well, that power supply is still attached to the capacitor, so it's going to charge it back up. So that's why we can make it so that we can provide the energy to the chip really fast, and also still always have a little bank here of energy for that chip. Another thing this does is it also helps eliminate ripple, voltage, or noise in your voltage supply. Because unlike what you might think here, we might say, oh, a DC voltage, if we look at this as far as this is the voltage and this is time, and if we have a DC voltage, we're saying, okay, well, it should be just constant flat like this for, let's say, maybe 9 volts. But in reality, it's probably not like that. It might be something like this. And that's blue line there is not a constant 9 volts. It's got something called ripple, or it might just be noisy, and sometimes they call it dirty power or unclean. And so this capacitor can also help eliminate that noise, because again, basically this chip is drawing from that capacitor as opposed to having to go all the way back to the power supply. All right. Now, the important formula we want to come away from here, though, is that this here is the formula for determining the energy stored in a capacitor. And then we also have this formula right here. Those are the two critical formulas for this video. So we'll end it here. These last several lessons have been a little bit longer than I really like to make them, but I just get so excited about this information, and there's so much good things, information we need to talk about. So I'll try and do better on making them a little bit shorter, but sometimes you just have to make them the length they are in order to cover the material.